Hey everyone, this is Chris Dingman, the Math and Science Explainer. And this video covers the vertex form of quadratic functions. And you can watch this video on its own, but it's also the second video in my series on quadratic functions and parabolas. So if you want to watch the series in order, which I recommend, the video to watch before this one is Introduction to Quadratic Functions and Parabolas. All right, this is the second lesson on quadratics and parabolas. In the last lesson, we were talking about this right here. We were talking about how, in general, functions are things that have inputs, which are usually an x, or often an x, and outputs, which are often a y. And quadratic functions are the kind of function where you have the highest power of x is an x squared. And we talked about the simplest quadratic function, which is here in the black box. That's where you just have an x squared. So you are now fully qualified to move on and talk about some more complicated quadratic functions and complicated parabolas. And they're not really going to be complicated. They're just going to be different. We're going to just add a few bells and whistles. All right, so let's take a look. So we've got our simplest possible quadratic function, which is y equals x squared. And it could also be written in function notation, which is f of x equals x squared. So f of x is exactly the same as y, no difference whatsoever. Well, obviously there's a little difference, but in terms of just f of x is an output, y is an output. So you can think of this whole thing as a y. All right? So we're talking about the simplest possible quadratic, which makes the simplest possible parabola. All right, let me move this over and make a little room here. Now, let's talk about a variation on this quadratic function and therefore a variation on the parabola that it makes. Let's say we took the basic quadratic equation y equals x squared and we just added a 3. What would the graph of that look like? And once again, remember, what's the connection between an equation, x's, y's, numbers, pluses, minuses, and some line over here on a graph? What is the connection? Well, just to quickly remind you, the graph is going to be an infinite number of dots or points that you get from plugging numbers in for x and getting out numbers for y. So just to do some real quick examples here, we make a table of values. We start plugging some numbers in for x. Let's put in -2 for x. What does that give us? 7. Let's plug in a +3 for x, and let's do it this time with the f of x notation. All right, so when x is 3, f of x or y is 12. Okay, so we can plot those points. -2, 7. Let's just say it's about right there. And then 3, 12. Let's say it's about right there. And then if we kept plugging in points, etc., and plotting those points, we would see that they would do something like this. They would make a parabola that was simply the old parabola moved up 1, 2, 3. So we call this the vertex where the parabola turns around. We'll get into that later. So notice the vertex is up 3, and the whole parabola, in fact, has been moved up 3. And you might have guessed that. Kind of makes sense. We added a 3 to the original function. And that, in fact, is the pattern. So you can quickly tell what a quadratic function looks like when you add a number to the x squared. It's just what we call the parent function, the simplest one, moved up or down by that number. So let's look at another example. Say we had the quadratic function y equals x squared minus 4. Well, if we made a table of values and started plotting the points, we would see the points started to follow a pattern that looked like this. And when we connected all those points, or filled in the infinite points in between them, we'd get this parabola, which is the old parabola now moved down 4 because it's a minus 4. So if we call that thing we're adding to the x squared k, for some reason textbooks like to use that letter k, it could be any letter, k stands for some number you're adding to x squared. So here k is plus 3, here k is minus 4. The rule is that the parent graph, this most basic parabola up here, will slide up k units if k is positive, or down k units if k is negative. So up k or down k. So there's your first little rule for how doing things to the simplest parent graph, in this case adding a number, how it affects the way the parabola will graph. Now, how does the graph respond when we add a number to the x before we square it? Let's take a look at that next. Okay, here's our simplest possible quadratic, which makes the parabola going like this, and then goes on forever. That's what the arrows mean. And its vertex is there at 0, 0, otherwise known as the origin. What happens if you add something to the x, let's say a 1 this time, before you square it, then you square it? That's still a parabola because it's going to end up squaring that x, and I told you a parabola or a quadratic is a function whose highest power of x is a 2. It can have lower powers, but the highest power is a 2. So we still have a quadratic. Again, if we were to make a table of values, I'm emphasizing this over and over because I don't want you to lose touch with the basics, which is the connection between an equation and a graph. The connection is that table of values, the series of dots, series of points. All right? So if we plugged in x's and got outputs for y's, we would see this. And we'd see that if we could do infinite points, they would smear into a parabola that looked like this. And we would see that the vertex was now back at -1. That might have surprised you because we added a 1 to the x. But we would see, if we did the table of values, that we'd actually end up back there. So the pattern is, well, let's do another one. I'll do it with f of x notation this time. I just want you to get used to seeing it both ways and just understand that it doesn't matter really which way we feel like writing it. Let's say x minus 5 squared. And this time, I'm going to just do maybe 1 or 2 points because I feel like boring you. I'm going to put in a 5 for x. So that means f of 5. F of 5 is 0. So notice when x is 5, y is 0. That's a point, right? 5, 0. 1, 2, 3, 4, 5. That's going to be a point. Let's do 2 more. Let's put in a 6. Looks like we output a 1. So 6, 1 is right there. And if we did a 4, we'd get a 1. So 4, 1 is right there. And if we kept going, you guessed it, we'd get this. If we wanted to just keep plugging in lots and lots of points, we'd get that pattern. We'd connect them all like this. And we'd see that the parent, what I'm calling the parent, it's sometimes called the parent graph, and these are its children, so to speak. We'd see that this new graph is the parent graph now shifted to the right by 5. So the pattern for this is, if you add something to the x before you square it, and let's call the thing you add h this time, textbooks like that letter, for that slot, the effect of adding something there is to move the parabola horizontally now. And it's also the opposite of what you'd think. So if h is positive, the parabola slides to the left in the negative direction. If h is negative, the parabola slides to the right in the positive direction. Now let's talk about combining the two kinds of shifting or sliding, or technically translations. In other words, let's combine the up-down movement with the right-left movement. All right, and then this time, just for kicks, let's also label this axis f of x, because that's the other way you could see it. So, again, we've got our parent function, our most simple parabola, y equals x squared. That looks like this. When you combine the two kinds of shifting that we just talked about, the up-down and the left-right, you just get both. So let's look at an example. Let's say we wanted to add a 3 in here before you squared it, and then over here we wanted to subtract a 2. Well, as you might guess, if you did a table of values and started putting in numbers and getting outputs, you would see something that had been, remember, shifted down 2. That's what this does. That's the vertical shift or translation down. And this would be the opposite in the horizontal, the opposite of 3. So left 3. So our new parabola would be left 3 and down 2. Our new parabola would have a vertex here. That would be a point, and then if we kept plugging in points and getting outputs, we'd get this. And if we did it for a super long time, we'd get infinite points, which would smear into a parabola. All right, so we've learned now how to look at a quadratic, at least if it's written like this, and we've learned what effect that will have on the graph of that quadratic. In other words, how the basic parabola will change. Let's look at another example. What if it were, I'll do f of x notation this time, f of x equals x minus 7 squared plus 1. So we're subtracting a 7 before we square it, and then we're adding a 1 after we square it. We would see points that started over here at 7, because this is a negative 7, so it shifts right 7, and then up 1. We'd see that point. That would be one of our input outputs. And then as we kept inputting x's and getting outputs, we'd start to see points doing this. And all the points would run together and make a parabola. And the parabola would be the parent or simplest function up here, shifted right 7, up 1. All right, we call those shifts translations. And they can be either vertical or horizontal. All right, now let's talk about that point I've referred to a few times, the vertex. This point where the parabola turns around, we call the vertex. It's the kind of key point in all parabolas. All right, let's write that down. And let's write what the coordinates are of the vertices, that's plural for vertex, vertices, of these three parabolas. The coordinates of the vertex of the orange parabola are 0, 0. That's what that point is, 0, 0. The coordinates of the vertex of the green parabola are negative 3, negative 2. And the coordinates of the vertex of the yellow parabola are 7, 1. So what I want you to notice here is that you can look at this graph, you can look at this function and actually read off the vertex, right? Notice it's the opposite of that number for the x, that's the x coordinate of the vertex. And it is that number exactly. That's the y coordinate of the vertex, right? And we could actually write that parent graph, that that simplest parabola this way, we could say that's y equals x plus 0. That's just x, right? So I haven't really changed it. Plus 0. So notice that, again, 0, 0, that works, the same pattern works for that. So these three quadratic equations are written in what we call vertex form, because you can read the vertex of the parabola right off the equation. Now you may know this, or you may have watched my video introducing you to parabolas, but parabolas can be skinny or wide, they can face up or they can face down, and you might have noticed that all three of the parabolas I wrote here are all the same width as the parent graph. At least they're supposed to be. And the reason they're all the same width is because they all share a number in common. And the number is invisible. It's the famous invisible 1, and it's right here. We don't write the 1 typically there because it doesn't affect the equation. Multiplying by 1 doesn't change anything. But you should imagine a 1 there. And this is often the case in math. There's invisible 1s hiding everywhere. You know, I could put an invisible 1 really in front of anything. Could put one here or here, and it wouldn't affect anything. So now we're going to talk about what if there's something besides a 1 out front there, and how does that affect the way the parabola looks? So let's take a look at that. That's going to be the final piece of the puzzle in vertex form. All right, so let's make our axis. And again, I assigned a y and an f of x to that vertical axis. They mean the same thing. And let's look at our parent parabola or parent quadratic. And let's remind ourselves what that looks like. So let's do a table of values. Let's stick in a number 0 for x. We get an output of 0 for y. Let's put in -1 for x. We get a 1 for y. Let's put one more point in. We'll put a 1 in for x. We get a 1 for y. Let's plot those points. 0, 0, -1, 1, 1, 1. All right, so here's 0, 0. Here's -1, 1. I'm being a little more exact. And here is 1, 1. All right, and then if we kept plugging in points from here to eternity, we would get infinite points. They would smear together into a parabola that looked like this. All right, now, instead of adding a number to the x squared or to the x before we square it, this time we're going to multiply out in front. Okay, so we're multiplying now, not adding. Let's multiply by the number 3. All right, we're randomly multiplying by 3 here. Let's make a table of values. Let's put in the same points we put in for the orange parabola, the parent graph. First, we'll put in a 0 for x. We get a 0 for y, so 0 in, 0 out. Let's put in a -1 for x. We get an output of 3 for y, so input -1, output of 3. One more, don't worry, almost done. Let's put in a 1 for x. We output a 3. Again, input 1, output 3. All right, let's plot these points. The points are 0, 0, -1, 3, 1, 3. So we come over here, 0, 0, overlap, same point. -1, 3 this time. So we're going to go back 1, up 3. 1, 2, so we're right about there. And then the next point is 1, 3. So we're moving to the right 1 and then up 3. Mirror image on the other side. So if you kept plugging in x's and outputting y's, you would get these points roughly. And even though you're tired of hearing me say it, If you plugged in infinite points, you'd get infinite coordinates. They'd look like they smeared together into a parabola. And that parabola would look like this, roughly. So we're getting a narrower parabola. So it looks like when you multiply out in front of the x squared, in this case with a 3, it changes the narrowness of the parabola. Let's do one more example. Let's say we multiplied out front by a fraction this time. Say we multiplied by a half. So now we have y equals 1/2 times x squared. Real quick table of values. Plug in a 0 for x. We get a 0 for y. So plug in a 0, output a 0. Plug in a -1 for x. We get a 1/2. So plug in a -1, output a positive 1/2. Last one, input a 1 for x. And we get a 1/2 for y. So input a 1, output a 1/2. Okay, now let's plot those points. First point is 0, 0. And it looks like we're still right there on the origin. Next point is -1, 1/2. So -1, 1/2, we're in there. And then 1, 1/2, we're here. And then if we plugged in a 2 for x, we'd get 2 squared is 4, 1/2 of 4 is 2. So we'd get over 2, up 2. And the same thing would happen at -2. We'd plug in a -2 and get a positive 2. So here's the parabola for the 1/2 x squared. Notice that gave us a wider parabola. So that number out in front of the x squared being multiplied affects the narrowness or width of the parabola. And remember, there was an invisible 1 in front of our original parent function. So if that's sort of the medium width, let's say we call 1 medium width, anything bigger than 1, like that 3, is going to make it narrower. So higher numbers make parabolas narrower, and then anything less than 1 makes them wider. What if that number out in front that's being multiplied by the x squared were negative? And let's take the simplest possible example of -1. So in other words, what if we had not y equals 1x squared, but -1x squared? And normally you wouldn't see the 1, you'd just see the negative sign, right? Those two things mean the same thing. Invisible 1. All right, quick table of values. Quick plug in 0 for x. We get a 0 for y, so input 0, output 0. Let's plug in 1 for x. We get a -1 for y, so input 1, output -1. Last one, -1 for x. Now be careful, right? Because we're sticking in a -1 for x, and then there's this other negative hanging out outside there. So -1 squared is 1, and now we get -1 again. So input a -1, output a -1. All right, let's throw this over on the graph. Again, we've got 3 points to plot, 0, 0, 1, -1, -1, -1. So that's 0, 0 right there, 1, -1, and -1, -1. So the parabola just flips down. And that might have been what you expected. The negative just flips the parabola vertically. And if you wanted to have a negative, say, with a number, like let's say -1/2, that would just take our 1/2 x squared parabola, which was up here, and reflect it. It's called a reflection, technically. It would reflect it down. Same width, because it's 1/2. The 1/2 affects the width, and then whether it's positive or negative affects whether it's facing up or down. So I'll just write that new parabola, that black one, as -1/2 x squared. And that's it. That's the final tweak you can make on our basic parent parabola, or quadratic, in order to change the way the parabola looks. So now we know how to move the parabola around by moving its vertex, like over 7, up 3. And we know how to flatten it out or reflect it vertically, or stretch it narrower. So notice that the number being multiplied out in front, let's look at the 3 here, that number is not being squared, right? And I say that because the final vertex form is going to look like this. It's going to be some number, usually called a, outside the parentheses of x minus h all squared. So the a is not being squared inside there, plus k. That's called the vertex form of a parabola, and you'll see that it combines all 3 of the tweaks that we talked about: the k, the h, and the a. And let me write an example underneath that. Now we know what every one of those numbers, a, h, and k, does to a parabola. The first one we learned about was k. The k moves the parabola vertically, a vertical translation or slide or shift. The h moves the parabola horizontally, and that we could call a horizontal translation or slide or shift. And then the a out front is the multiplier we just talked about. That affects the narrowness of the parabola and whether it's facing up or down. Positive up, negative down. So this is the vertex form of a parabola. If you can get a parabola or a quadratic looking like that, and here's an example, you can read off the vertex and you can know how narrow it is, and you can know whether it's facing up or down. So the vertex is going to be hk. So in the example I gave below that, the vertex is going to be 5, 1. Now notice, remember the h, the horizontal slide, that h, we said was the opposite direction. So notice the formula works because when we see this negative 5, notice the actual vertex is positive 5. And then the k part, the y coordinate of the vertex, is straightforward. It's just the 1. It's what's right there. All right, and then the a value in my example is a 3, is telling us that this is going to be narrower than that standard parent graph, and it's going to be facing up because 3 is positive. So let's move that vertex over by the vertex form. All right, let's end by doing an example using the full-blown vertex form, and we'll see how this all works. So let's move this up. Make ourselves a little room, and now let's make up an example. Say you saw this equation, and you're asked to say what this parabola looks like as a graph. So let's draw the graph. All right, what does this parabola look like? First thing we'll do is find the vertex. The shortcut is simply the vertex is this number here for the y coordinate or the k value, and it's the opposite of this number here for the h value or the x coordinate. So it's not +2 that's written, it's -2. That's all there is to it. That's the shortcut of what the vertex is by looking at the equation. Now, if you want to know why that works, I'll show you real quick. It's because this isn't written as x minus something, it's written as x plus something, x plus 2. If we want to write it as x minus something, we could say x minus 2. You see, now it's written in that minus something form, and we can see that h is -2, which is what we have written up here. And if you don't feel like remembering that, just remember that it's the opposite of the number that's in those parentheses for the x value of the vertex. So let's just plot that, -2, 1. That's right here. Now, does it face up or down? It faces down because a is -1/4. The negative part tells us it faces down. And how wide is it or how narrow is it? Well, it's 1/4, which is less than 1. Therefore, it's wider than that standard parabola that we started with. So our standard parabola would go over 1 in the horizontal and then down 1 or up 1 in the vertical, depending. In this case, down. This is what the standard would do. But ours is wider. It goes over 1 and only down a fourth. So I'll go over 1 and then down a fourth. And then it goes the other direction to the right 1 and down a fourth. All right? And then if we plotted infinite points, the parabola would look like this. Roughly, anyway. Now, I'm just going to sketch that parent graph, the simplest parabola. Remember what that was. It was y equals x squared. That was a parabola that faced up, had its vertex at the origin. It went over 1, up 1, back 1, up 1, and then it looked basically like this. So I just want to point out now that I've talked about that h and k kind of in two ways. I've called them shifts, right? Like a slide up and a slide left or right. But I've also called it the vertex. And it's both, okay? So if we think of it as a slide or shift, then we're starting with this parent graph. And in the case of the parabola I drew here in orange, we're sliding it back 2 and up 1. But notice that's also going to tell us what the vertex is, -2, 1. So the h and the k are both vertical slides or horizontal slides, and they're also the location of the vertex. All right, that's it for this video on the vertex form. If you're watching this video in my series on quadratic functions and parabolas, the next video is standard form of quadratics.